All right, Ryan. So this is topics 9.2 to 9.3, part 2, confidence intervals for the slope of a regression model and justifying a claim about the slope of a regression model based on a confidence interval. So now that we know about the sampling distribution that leads us to the math that we can do to construct a confidence interval, let's break down the process step by step, okay? So obviously, when we are constructing a confidence interval for the slope of a regression model, just as with all of our confidence intervals, there's 4 steps in our process. So our first step is name the procedure in context. So this is going to be a TCI for the slope of the regression model, relating blank and blank for the population of all blank. So because we don't know the population standard deviation, we have to estimate with S, then this is going to make it a T confidence interval, just like we did for means. And then obviously you just put in your context. So the slope of the regression model relating temperature outside and number of cricket chirps for the population of all days in the winter of 2020 or whatever it is. Okay. Then step 2 is where this gets really tough, because step 2 is state and check our procedures, right? And there are a lot. So when, I had the same slide in there twice. When we are stating and checking our conditions, we're going to use S lines. It's going to be a lot longer than sinning, and definitely a lot longer than SIE for our chi-square tests. Chi-square tests are really nice and easy, and then it gets really, really tough right here at the end in this last unit, but it's not bad. So again, we're going to use S lines to state and check our conditions. So the first S is the same S we've always had. The data need to come from an SRS, from the population of interest, or from a randomized experiment. And obviously our check, we just have to state where the data came from, as they told us in the question. So that's an easy one. L is new. When we're doing linear regression, obviously the L is going to stand for linearity. So the actual condition is the real relationship between X and Y is linear. So for the population of all, whatever X and Y are, then the relationship is linear. To check that, we just graph the scatter plot of our sample data, or we can graph a residual plot of the sample data. If our scatter plot is nice and linear, or if our residual plot shows no apparent pattern, no curves or anything, then it's likely the population is also linear. So just depending on whichever is easier. Sometimes, you always, I think, would want to look at the scatter plot first to even see if you have a linear relationship to work with, but sometimes there's a slight curve that you can't see until you check the residuals. But the good news about all of these conditions is that usually, number one, usually these kinds of questions don't even come up on the AP test. I think our course description this year says this is only 2 to 5% of the overall AP exam. And when they have had these kind of questions in the free response, then they usually give you all of the graphs. You don't have to make them. So you can just look at the residual plot or the scatter plot that they gave you and say whether it looks linear or not, which is what we're going to do in our example in the next video. Okay, our I then is same as it's always been. When we're sampling without replacement, the observations need to be considered independent. And so, of course, we just check that our lowercase n is less than or equal to 10% of capital N and explain what that means. So that's nothing new. Now the N and the E go together as one condition. So our NE condition actually says for a particular value of X, then the responses, the Y values, are approximately normally distributed. So, if we had the number of cricket chirps predicting the temperature, then, you know, for a set number of cricket chirps, maybe 5 per second or something. I don't know how fast crickets chirp, but then every time we sampled 5 per second as the number of cricket chirps, and we looked at what the temperature was right then we'd end up with probably a couple different temperatures, right? And so all of those responses, those Y values, should be normally distributed. Ideally, we would check the residuals for normality at each possible value of X, but because we rarely have enough observations at each X value, we just make one graph of all the residuals from the different X values to check for normality. In other words, here's where my NE comes from. We need an approximately normal distribution of the errors, the residuals. So that's why I'm using that NE, because it spells lines nicely, S lines, but that NE is for normality of the errors. So our check is we're going to make a box plot or a histogram or something of the errors, the residuals, and show that that's approximately normal. So this is not a residual plot. We have to calculate the residuals in our calculator, but then we graph them as just a good old box plot or a histogram. And then our last S, oh yeah, sorry, I put a graph in here first, I forgot. So you can see for each of those different X values, the Y values that you get out should make a nice normal approximation. And it's kind of hard to see that those are normal. They look a little squished, but it's because it's sideways. They're trying to represent a 3D graph. But so for the center of each of those normal distributions, right, for each of those different X values, those should be on that population LSR line. So that least squares regression line for the entire population. Okay, and so for the last S, that's what this is saying in the box. For any fixed value of X, then the standard deviation of Y should be the same. So for each of the different X values, we should have about the same standard deviation. So they said for any fixed X, the responses Y follow a normal distribution with standard deviation sigma. So we should, for each of those normal distributions, have the same standard deviation. So the standard deviation of all those responses, all those Y values, should be the same for each X value. And so I said then our S condition is that the standard deviation stays the same or does not vary with X. So that's my S. And the check then is we graph a residual plot and look for fanning. We do not want to see fanning, because if you have a residual plot that starts out pretty close together and then starts getting spread out farther and farther, then obviously for each of those X values, we don't have the same standard deviation for the Y's. They're getting more and more variable. That's why the residual plot's fanning. So we do not want that. If they're the same, then we should not see any fanning in our residual plot. Okay, and so that's our step 2, that S lines. That's a lot of conditions to state and check. Now we can go on to our step 3, which is our do the math. And so to construct a confidence interval for the slope, we're going to start with our sample statistic with means. You know, we started with X bar, with proportions, we started with our p hat value. For slope, obviously, we're going to start with our sample slope, our least squares regression slope, B. And then I said already this is going to be a t distribution because we don't know the actual standard deviation. So our formula we talked about in the previous video was sigma over sigma sub x times the square root of n, right? We are going to, because we don't know the value of sigma, have to substitute in S the sample standard deviation of the residuals over Sx over, and this actually is going to turn into n minus 1. If you want to know why, Google it, because that's way more than I want to get into explaining right now, but that's what we're going to have to use as our approximation because we can't actually find sigma. And so that whole formula is usually called SE sub b, the standard error of the slope. So I'm going to take my t critical value times the standard error of the slope. Okay, so that's the math that we're going to be doing. And obviously we need to state our degrees of freedom too. Sorry, I wanted to go grab my book so I could see the formulas again. So our degrees of freedom is just the number of observations minus 2, because we're dealing with the 2 different variables, x and y. So we have 2 less things that can vary for us. So n minus 2 is our degrees of freedom. Okay, and again, if you want to see why that is, you can Google it because that gets kind of complicated. All right. So that's the only math that we have to do. And again, our calculator is going to help us out with this. So we're not going to have to really do much of this by hand. And so then our step 4 is our conclusion and context. And it's been a while since we talked about confidence intervals. So let me remind you, it starts with, based on this sample, I am whatever % confident that the true or the slope of the population regression line, or I could say true slope of the population regression line, is between blank and blank. And I would put it in context. Okay. So that's all the steps there are in constructing a confidence interval for the slope. And I'm going to give you your own assignment, so just ignore this one because I'm going to take pictures out of the newer edition of the book. But I think I'm going to put the homework after the 3rd video because I haven't looked at the problems in the book yet. So that does not apply to you. And I will talk to you again in a few more minutes.